I was going to do a double act with my colleague Kevin Allen. Unfortunately, he sends his apologies. He can't be here today. He'd love to be, I'm sure. I hope I can do him credit. It was going to be a double act. You're going to have to put up with me, I'm afraid. I'm going to talk about the optimisation of a differential, automotive differential. We've used more colloquial differential because if we use drive unit, you'd all be expecting electric motor. And reflecting on it today, after over 30 years in and out of automotive, this is probably the last time I'm going to talk about an internal combustion engine. End of an era, if you like. So what I'll go through is the background to the challenge we faced, scoping the challenge, why it was such a problem, how the team solved it, and did it work. That's the structure today. So stepping forward, it's about the Range Rover brand. 50 years old in 2000. You're familiar with them. We still put that slide up. Kevin said, I remember the first time I went to one of those as a child. It was that colour, and he talked about the smell, the noise. You can imagine it. Would you accept that today in a car? That impact on him. I remember it slightly older. One passed me in the back streets of Wantage. Somebody said, hop in. And I remember it leaning more than my motorbike. So it's evolved. And there is just so much more stuff in a car now. You think about we've got infotainment systems, 7-seat aircon, off electronic intervention, air suspension. It's a completely different product, different world. And what happens, our story transitions this anniversary here. 2021, we release the next generation of this product. And it's an evolution, a revolution into what we call modern luxury. We were back there about 2017, preparing for this. One of the concepts that comes in is the tranquil cocoon, tranquil space. It's no longer a car. You step in, you close your door, and it shields you from the world. So it's a whole revolution in the customer experience of the car. It's got to be quiet, refined. For everybody, anything that makes any noise in the car, you've got to step your game up to improve what you're offering. So just to align what we're looking at, we talk about the rear differential in the car. It sits, if I can point, in the rear suspension. I'm sure you're all familiar with it. And it consists of a differential, which isn't actually very relevant to our story. All it is 4 bevel gears that allow differential speed under torque of the car. What really matters is the crown and pinion that take the torque through 90 degrees. Now, 2 things there. One is you've got gears meshing. Doesn't matter how well refined your product is, the meshing of the gears will create high-pitched noise if you don't get it right. And it comes through about 600 or 700 hertz, and it absolutely is impossible to solve if you get it wrong in development. So it's a big issue. The other thing is we differentiate, no pun intended, the gear ratio of the car in this unit. So if we've got a light car with a big torquey diesel, we have a very low ratio. If you've got a big car with a small petrol engine, you have a high ratio. And that means that the torque vector rotates, so the optimum mounting position is different between the 2 systems. We put it in a casing, all sorts of electric motors on it, to vector the torque, disconnect it for efficiency. And it's this prop shaft rotating here that generates the next 2 load cases. It's a long, flexible shaft. It has a rotating imbalance. If you then don't isolate that effectively, about 40 to 50 hertz, the whole car shakes itself to pieces. It really is quite an impressive load case to deal with. And there's also a torsional vibration from the engine firing coming down the prop, exciting the system. And that typically occurs when you're accelerating in low RPM. There's a sort of vibration in the car. You put your foot down and you get a thrum and it goes. But the bandwidth we're dealing with is about 30 hertz to a kilohertz of frequency range. We're trying to engineer the system over to isolate this. And finally, we mount it into the rear suspension and the driveline using some rubber mounts. What we're talking about today is how we engineered a new solution for that system, including the drive unit, the differential, as one entity. So moving on, why did we have such a problem? Well, the last time we did a differential was 2009. And that was very much for a sports car. So one of the key enablers you had to do was enable spinning the wheels. You're doing a new V8 engine, more performance. The customer wants to spin the wheels from the lights. That's the main customer feature, as well as improving the refinement. And over time, we've gone from cast iron to aluminium. Aluminium is lower inertia. For a given force, you get more vibration, more noise. And then we'd put smaller engines into SUVs. That means everything's spinning faster. The gear meshing gets to a higher frequency. You further separation from the low frequency masking. You get more of a problem. And actually, I realised on the way down in there as well, we removed torque slip from torque converters. So we really were reaching, at this point, the end of life of that system. It was great here, not really future-proof. When you look at the masking noise level, the noise that hides what we're creating, although people picture it coming down linearly, there's going to be a transition. And that is, we were working on we knew the current product. We're working on fixing every acoustic weakness we can find in it, but also active noise cancellation for road noise and driveline noise up to 1,000 hertz becomes standard on the car. So all the noise hid, all the things we did, goes away. That was a challenge, and it wasn't going to be evolution. We had to completely rethink how we optimized and integrated the mounting system and the differential to get ready for this new world. Really significant challenge. So to do that, the first thing we did was build the team and look at what we're working in. Myself and Kevin, we sit between the attribute teams to look at the noise and performance of the car, and the hardware teams who actually deliver the bits you buy. And our job is to understand the needs and function of both of those. And we talk across each other between the driveline and the anti-vibration mounting. What came out was really you're working 3 discrete domains. The refinement team work in the frequency domain. They do all their models, steady state, force, transfer function, noise. The performance feel, the sportiness of the car work in time. What they look at is from when you put the pedal down, when do you feel the delay to car accelerating? That is the performance feel. Then it's how quickly can you make the car accelerate, because that's your 0 to 60 time. That's the sportiness of the car. So all their metrics are in time. So we're already working 2. Then we've got to package. We've got to make sure we constrain the unit within the package constraints. And that's spatial. So when you start thinking about a problem to optimize, I've got 3 different domains I need to bring together and get to talk to each other to come up with a common solution. So we decomposed it into this way. We've got 3 MVH load cases we talked about: gear meshing, combustion forcing, prop shaft imbalance. The PED attribute is vehicle acceleration delay. Package is clearances, and that goes into the pitch and roll of the unit under torque. We also have error states, and that's more of an ownership thing. That these guys say, I can set a target. For me, I have to make sure that we don't, when you put torque on, get a thud, dunk, really upsets the customers, or the car stalls and hesitates. That's the error states. So that was scoping the problem and how we did it. Sorry, I missed something on this slide. No, come on to it. Sorry, get better to it. So we knew we had an optimization challenge. And then the question was how to optimize. It's a bit of a twee slide, but there's 2 fundamental approaches. You can map a design space across multi-attributes and hopefully find a common solution that fits everybody's needs. But that means that running a huge number of solutions across multiple platforms and working out how to bring them together. It's very labour intensive. We did it in 2009. There we had a really defined strategy, and it took months. Really don't know how to answer this problem. Or you can use something like a gradient solver, which you automate, you set it a challenge, and it works its way downhill to an optimum, which is great if all paths lead to Rome, as they say, and you've got a common solution. If you look at this, if I want to find the lowest corner, where I start gets me a different answer. So there's a trade of investment of time and the fact that you may not get the right answer first time on the solution techniques. We'd looked at it and decided probably the best solution was a gradient solver, accepting we're going to have to do multiple runs and iterate. It's not going to be run a solver, get an answer. This is going to be a long-winded, iterative process. The question was how to get the skill set. It's a big problem. None of us had ever run this system before. And then we had a bit of serendipity that our research team had been working with GRM on a similar project where they'd been optimizing the structure of the drive unit. That was their main focus. How do you lightweight that structure? But to do that, they had to consider the mounting. Because if you moved the mounting, you changed the mass properties in there. So we were able to build on this. And they had two things. They had a relationship with GRM, which gave us access to an optimizer and experts in optimization. We had a team that understood us, that worked with us, they knew what makes JLR tick, and the team that were doing this stayed with us through the journey, so GRM had consistency of approach, and really importantly, they had budget. Because one of the big challenges we face always as engineers is getting money to pay for things, isn't it? So we had budget, we had a solution, and we had a thing to build on. Let's stop that. So what we then did, let's start decomposing the challenge in the teams. And he said, well, we can treat the final drive ratio as a noise factor. I've got 5 drive ratios to cover a saloon diesel to a great big SUV with a small petrol. And I can say, I've got 3 load cases for MVH, the prop out of balance, distortions, the gear meshing. I've got load cases for those. And in this, we were saying to the teams, you can't do what you've done before. You've got to rethink what you want. How are you going to enable us to do something different? You don't just say, well, it's like that yesterday. You've got to give me something else. So the teams really stood out. The MVH team said our targets are actually got driven by some real dips in the target. We can trade those. If you can't meet them, that's where we'll negotiate with you. The driveline joint team said, actually, we can give you more movement than we could before. We're going to double the amount you're allowed to move the drive unit. So suddenly, instead of having 2 degrees of movement, I've got 4. I've got twice the design space. He said, are you sure? Because if you get this wrong, it's a really big deal. Nope. We are absolutely sure. And the hardware team in the imbalance load case said, we've actually learned to balance props better. We can halve the imbalance forcing for you. So suddenly, I've got twice the design space and half the forcing in one of my key load cases. Beginning to get a real sight of a way forward. Then the other thing that happened was the PED team said, actually, when you look at a long SUV instead of a short sports car, stiffness in the drive unit mounting isn't really that critical to us. What matters, it's shown here, is a purity of response. So this is torque, rotation. So when you put torque on, it's got to be smooth, it mustn't inflect, and it's got to be at a soft end to the thing. So suddenly I've removed a major constraint. What I'm left with is a very challenging package constraint, because in the architecture we're bringing in rear-wheel steer and electric roll control, and they are placed at the front of the subframe, and I've got a very narrow portal to get the drive unit through. So I've got a pinch point in my system. I've got to make it move around in a very unusual way to try and optimize the system. So I've got some real enablers and I've got some real challenge. And you look at it, yeah, there's some things you can play with. Bounce span, it increases the stiffness. Move things further apart for a given rubber mount makes it stiffer, great. But the cantilever beam with the drive unit loses its stiffness as a cube of its length and it gets heavier. So it's not as simple as you think. So there's a number of interactions. If you make the drive unit bigger, it increases its mass. Great, I like inertia. But we buy metal by kilos, puts the price up. So we understood these interactions, but we're still left with 2 real tool sets to use. So it's not an easy optimization problem. Within that, we've also got our control factors. We've got the number of mounts. Then we do a 3 or 4 mount system working forwards. So that's what we're looking at working through. We had a moment with epiphany. The FEA can do MBS. It's called a rigid element. So if we now combine our solution into a flexible MBH load case and a rigid torque application in FEA, I now have one tool set to do all the solution I need. Quite simple. We take that, we'd run that solution across 5 drive ratios. So that's our balancing the system across all 5. We've now broken it down to 4 load cases coming in: the imbalance forcing and the combustion forcing and the gear forcing. Prop shaft torque, we did it at a very low torque and made it linear. Because the PED team has said we can just look at that purity of response, we broke that out as an overcheck. Removed it from the optimization. We actually had a screening spreadsheet in the middle, so you could quickly look at a solution and go, that's not going to work. Back, change the parameters of it, off we go. And then against those, we have a set of targets. So we've got the prop out of balance response. For each engine, you've got a unique target for its combustion forcing. You've got the gear wind response. You've got the pitch and roll angle we talked about for package, and we've got the displacement in millimeters. So we've now decomposed the whole thing into one solution set, and we're looking at the mount position, X, Y, Z. We did look at Z a bit, just to see if it did anything. Reality is, subframes are flat, you know we're going to mount to, and the bush stiffness. So you then say, that's great, I've got all that organised. How do I then pose this question to an optimizer? How do I make it efficient for the optimizer to understand the world around it? The first thing we did, we said, well, if I've got a pitch and a roll limit, that's a ratio. So I can now decompose that to be a pitch angle and a ratio of pitch to roll, which is how off the vector the mounting system is from the torque vector. Then we make that the objective, to minimise the pitch of the system, which is maximise the stiffness as my goal of my optimizer, making everything else a constraint. So it's got one target to go at and a series of constraints it can't violate, which for an optimizer gives it clarity. If you can throw multiple targets at them, but you're making the problem for it bigger. So what that boils down to is 10 concurrent FEA models running sequentially at the same time. By the way, the Flex model also has a full rear suspension in it. It's not a small model. It's a quite big configuration hungry. We have 16 design variables. It's moving around, trying to optimize the position and stiffness of the mounts to achieve these. The 4 load cases we talked about running through sequentially, simultaneously, and 65,895 unshored constraints. There's got to have not violated as it's doing it. The reason is that what you see as a graph, Genesis just sees as a series of numbers. It doesn't know it's a graph. It just knows at this point I must meet that number. So we have a way forward. We can optimize the system. So looking at it, what happened? Now Martin did this slide for me. Tried to visualize for you. He's got a new talent of animation. What does it look like when you run an animation like this? And what you can see is we can move the mounts, and they're actually moving with the structure and in the subframe. So as you move something, the drive unit differential is changing stiffness with it. So it's in the system. If I move the mount outboard, the frame bit gets stiffer, but the drive unit gets more flexible. So I'm compensating for that effect. I'm compensating for the change in inertias, how that affects a low frequency response. We then play with the mount stiffness of all 4 mounts in all 3 directions, optimizing them, making sure that none of the constraints are violated. So the optimizer will throw out any solution that violates a constraint across 5 different driveline ratios, trying to minimize the pitch of all of them. So we've gone from a very complex multi-domain problem into a single solution set. Then what does this mean? I like this slide. Martin sent it to me at the end. I asked him for an animation. It's a bit of a dig. What does this mean? Well, we did the optimization. We defined a solution. And we went our separate ways. And with hindsight, it must be you're working live at GRM. You do work for people, they disappear into the ether. And the success is we delivered what GRM defined. Simple. Sounds easy. 5 years later, what rolls off the car is what we defined with the team. And that's what it looks like. It is actually the hard points and targets, stiffness targets that were defined from simulation. Delivered now, I think we've built about 100,000 cars with this in. It's in 2021, won new accolades. But the real question is, did it work? Did it deliver what we wanted, which is the performance of the vehicle and the refinement? And if just segue onto the end, we'll see what it shows us. Probably the last big project in the internal combustion engines, we set out to deliver silence. Watched Top Gear, and it really was quite an emotive moment for the team. No, we set out to do, and we got a public affirmation of what we set out to achieve. So to answer to GRM, yes, it worked perfectly. Thank you.